There is a valve that costs $10 in raw brass to make. It has no rubber, no springs, no washers, and no seats to replace. It seals tighter the harder the water pushes against it. Victorian plumbers installed them by the millions. Not one was designed to drip. We did not abandon this valve because it failed. We abandoned it because it never needed a replacement part. A valve that never leaks does not sell O-ring kits and does not bring the homeowner back to the hardware store every 18 months. This is the story of the ground key valve, the precision brass fitting that sealed itself with physics, and why the plumbing industry buried it under a mountain of rubber washers. In the ruins of Pompeii, archaeologists have uncovered bronze stopcocks with a geometry that feels eerily modern. Each artifact, now labeled in museum catalogs with accession numbers like 2019.142 or 1988.67, reveals the same principle: a conical bronze plug ground to fit a matching seat, turning inside a lead-lined channel. The Romans shaped these valves with a taper close to 1 in 6, about 9.5 degrees, a standard that would survive for nearly 2,000 years. Excavation reports from Pompeii's waterworks describe seats that still bear the marks of repeated use, their surfaces polished by centuries of opening and closing. Even after the eruption, after centuries underground, the conical ceiling faces remain intact. The Museum of London holds a Roman stopcock accessioned in 1988 that still fits tightly in its socket. The patina has darkened, but the engineering is unmistakable. The bronze key can be withdrawn, cleaned, and reseated. No rubber, no washers, no springs. The only thing standing between the city's water and the outside world was the precise fit of 2 metal surfaces, pressed together by hand and tightened by the very pressure they controlled. These ancient devices did not rely on disposable parts. Their longevity is not theoretical. It is proven by the survival of the artifacts themselves. The same conical geometry, the same reliance on pressure to enhance the seal, would reappear in the brass foundries of Birmingham 18 centuries later. The Roman stopcock stands as a silent witness. The idea of a self-sealing metal-on-metal valve is not a Victorian invention. It is a rediscovered technology, refined by generations who understood that physics, not planned obsolescence, could keep water in its place for centuries. On February 12, 1792, a new chapter began in the heart of Birmingham's Foundry District. Patent number 2470, filed by the partnership of Matthew Bolton and John Fothergill, described a stopcock unlike any before it. A brass body precision ground to a 1 in 6 conical taper, operated by a square key, and sealed without a single washer or spring. The original patent text was blunt in its confidence. The stopcock is ground in a taper of 1 part to 6, whereby the whole of the valve may be sealed with a single turning of the key. The drawing attached to the patent shows every detail: a simple, robust geometry, a cylindrical shell, a conical seat, and a plug that fits so tightly that water pressure itself forces the seal to improve as the system comes under load. This was not an experimental prototype. It was a design ready for industrial scale. Within 3 months of the patent, the Bolton and Fothergill ledger records a shipment delivered to the Corporation of London: 120 brass stopcocks, ground key, 1 in 6 taper, price £3, 2 shillings per dozen. This was not a local curiosity. Orders followed from Paris and Boston, each referencing the Birmingham pattern. The ledgers show a steady flow of finished valves, their destinations stretching across the Atlantic. The foundry's pattern plate, still preserved in the archives, bears the same measurements as the patent drawing. Guest and Crime's 1795 pattern book, Plate 8, would soon engrave the 1-in-6 taper into British engineering memory, describing it as the most perfect seal yet devised. By the close of the 18th century, the ground key valve was not just an invention, it was a product. The archives reveal a deliberate campaign: patent, manufacture, export. The design's simplicity was its strength. No rubber, no consumables, only the physics of brass pressed against brass and the confidence that water pressure would do the rest. The technical proof of this design's promise would come later, but the industrial intent is already clear in the records of 1792. A conical brass plug, ground to a precise 9.5-degree taper, does something no rubber washer can do. It turns water pressure, the very force that tries to break a seal, into the agent that perfects it. The geometry is not accidental. When the plug enters its seat, the taper multiplies the closing force radially, focusing pressure onto a narrow, almost invisible line of contact. With every turn of the key, that line becomes tighter, the contact area grows, and the valve transforms from a simple fitting into a self-tightening barrier. This is the genius behind the ground key valve. The surfaces are lapped, polished with fine abrasive until they mate so closely that a human hair cannot slip between them. Under a microscope, the finish reveals a landscape of micro-ridges flattened by careful handwork. Each time the valve is closed, the brass at the sealing edge undergoes work hardening. The grains in the metal, once soft and yielding at 60 on the Brinell scale, compress and realign, doubling their resistance to deformation. In laboratory tests, that rim reaches 120 on the Brinell scale. After repeated cycles, hard enough to resist scoring, yet still able to conform minutely to the opposite face. The result is a seal that improves with use. Unlike rubber, which flattens and cracks, the brass-on-brass interface adapts, hardens, and becomes more leak-tight as the years pass. The pressure inside the pipe, whether a trickle or 600 pounds per square inch, only drives the plug deeper into its seat, amplifying the radial load and closing any microscopic gaps. There are no springs, no washers, no parts to replace. The valve's integrity is written in its geometry and the physics of cold-worked brass, a design that, once set, asks nothing but to be turned. A brass ground key valve faces the pressure chamber, a relic of Victorian engineering, weighed and measured by modern instruments. The dial climbs past 100, then 400, then 600 pounds per square inch. Inside, a conical plug, lapped to a mirror finish, presses into its seat. The water, forced by the pump, seeks the faintest path to escape. Sensors track every molecule. The calibrated mass flow meter, with a threshold of 1/100th of a milliliter per hour, records no surge, no spike, just a flat line. Over 60 minutes at 600 pounds per square inch, the leak rate never rises above 0.05 milliliters per hour. That is one drop, less than half the volume of a single raindrop, in an entire hour. For context, a typical household line runs at barely 80 pounds per square inch. Most modern shutoffs are never asked to withstand more than a fraction of this pressure. The test is repeated. The valve is cycled open and closed 10,000 times, then repressurized. The readings hold steady. The micrographs, taken before and after the test, reveal a rim of brass transformed. Under magnification, the contact band glows with a denser, finer grain, evidence of work hardening, not wear. The surface, once soft at a Brinell hardness of 60, now registers double that figure. The line of contact, invisible to the naked eye, becomes a fortress at the molecular level. Industry standards for new valves allow 10 times this leak rate at half the pressure. Yet here, physics and precision machining do what rubber cannot. The higher the pressure, the tighter the seal. No washers, no springs, no disposable parts. Just a self-tightening barrier, validated by numbers that leave no room for doubt. By the 1850s, the ground key valve was the quiet force behind city life. London's waterboard records show entire mains beneath the Thames embankment, built around these brass stopcocks. On March 30th, 1852, the board approved 200 ground key valves, citing their proven durability and ease of maintenance. These were not just claims on paper. One valve installed in 1867 stayed in flawless service for 36 years, replaced only when new pipework demanded a different fit. Paris followed suit. In 1860, the city's water board ordered ground key stopcocks for the Canal de l'Ourcq. 3 decades later, engineers found those same valves still in place, their brass faces showing no measurable wear after years of mineral-rich water. Reports noted the only maintenance needed was a little grease on the key, no washers to swap, no springs to fail. Water quality tests at the valve sites found 0 contamination, a standard later rubber-sealed valves could not match. Boston's water department made the ground key valve its standard shutoff. An 1882 report lists them as the default, with crews trained to service the key-driven mechanism. Inspections in 1915 and 1940 found the original valves still sealing perfectly, untouched by corrosion, needing only the occasional application of grease. The Royal Navy trusted the same design as it shifted from sail to steam. Admiralty manuals required ground key valves for boiler feed and condensate lines, each one holding 800 pounds per square inch of steam, without a hint of leakage. In the engine rooms of ironclads, naval engineers, often overlooked, relied on the precise taper and lapped brass seat to keep water and steam safely contained. Pattern books from Guest and Crimes in 1902 set the standard, publishing exact dimensions to ensure every valve from Sheffield or Birmingham would fit and function identically, whether destined for a city street or a warship at sea. By the early 1930s, the economic argument for rubber was impossible to ignore. Brass, once the backbone of municipal infrastructure, now cost 12 pence per pound, while synthetic Buna N rubber, newly arrived from the chemical plants of Germany and the United States, could be had for 3 pence. Price tables from London Metal Exchange bulletins and Rubber Manufacturers Association reports told a simple story. A raw material cost 4 times lower, multiplied across millions of fixtures. A brass ground key valve needed half a pound of metal just to start. The new washer-based shutoff used a thin steel shell and a sliver of rubber, dropping the material cost to pennies. Manufacturers did not hesitate. In the pages of Plumbing Engineer, trade journals began to praise the economy and ease of assembly of the washer valve. The numbers in the ledgers were clear, but the cost-cutting ran deeper than materials. On the shop floor, the skills that once defined a craftsman, lapping a taper to within a fraction of a degree, reading the grain of the brass, fitting a plug so precisely that water pressure alone would finish the seal, became obsolete almost overnight. Trade schools responded. By 1960, apprenticeship curricula in both Britain and the United States had rewritten their syllabi. Where once students spent months mastering the art of hand-lapping a valve seat, the new textbooks featured torque tables for rubber washers and diagrams of cartridge assemblies. The Amalgamated Engineering Union's annual reports and Ministry of Labor returns recorded the fallout. A 45% drop in plumbing apprenticeships between 1935 and 1945. The old skills faded as quickly as the machines that once kept them alive. A feedback loop took hold. Fewer skilled hands meant fewer ground key valves produced, just as manufacturers, chasing the post-war housing boom, standardized on disposable designs. The new economy thrived on replacement cycles, O-rings, washers, proprietary cartridges, all destined for the hardware store shelf. The logic was not technical failure, but economic convenience. The ground key valve, with its promise of a lifetime seal and no consumable parts, had become a liability in a market built on planned obsolescence. What was lost was not just a product, but a body of knowledge, a way of thinking that valued restoration over replacement and precision over disposability. 1 trillion gallons of water vanish from American supply lines each year, lost not to drought, but to leaks. EPA's own reports trace much of this waste to the silent failure of rubber-sealed valves, the kind found in nearly every home, apartment, and office. Inside the walls, behind the fixtures, a slow drip begins. Not a burst, but a creeping seep, undetectable until the numbers appear on the city ledger. The scale is staggering. Enough water to supply Los Angeles for a decade, surrendered drop by drop to a flaw built into the system. Rubber, once hailed as a miracle material, cannot withstand the assault of modern water chemistry. Chlorine, added to keep water safe, reacts with the unsaturated bonds in synthetic washers and O-rings. Laboratory tests show a 30% drop in sealing force after just 5 years in chlorinated municipal water. The rubber hardens, cracks, and loses its grip. Each cycle of pressure and release widens the breach. Unlike brass on brass, which only tightens under load, these seals are doomed from the moment they leave the factory. The market has adapted, not by fixing the problem, but by making it routine. 70% of new residential valves now rely on proprietary cartridges, plastic and rubber assemblies engineered for rapid replacement, not restoration. Hardware stores devote entire aisles to repair kits, O-rings, and brand-specific cartridges. The consumer, locked into a cycle of recurring purchases, rarely questions why a shutoff must be serviced every few years, or why a device once built to last a century is now disposable by design. The cost is measured in more than water bills. Every failed seal means another trip to the store, another piece of rubber destined for landfill, another skill lost as the trade shifts from craftsmanship to cartridge swaps. The ground key valve, immune to chlorine, indifferent to pressure spikes, and built for restoration instead of replacement, stands as a rebuke to this engineered obsolescence. The numbers are not just statistics. They are the record of a choice, repeated millions of times, that trades resilience for convenience and leaves the bill for someone else to pay. Metal-seated valves remain the backbone of gas safety, their design mandated by law wherever high-pressure lines run beneath city streets. The UK gas safety installation and use regulations, enforced since 1998, require a ground key or similar metal-to-metal shutoff. British Standard EN 12567 details the geometry, 1 in 6 taper, minimum QZen 30 brass, and a leak rate under 0.1 milliliters per hour at 150 psi. Inspectors arrive with calibrated rigs, pressure decay tests, and the authority to reject any valve that fails the Victorian benchmark. Here, the ground key design is not a relic, but a living standard, trusted, where failure is not an option. In the West Midlands and Boston Seaport, heritage workshops preserve the craft. At the Heritage Brass Foundry in Smethwick, the master turner guides apprentices to lap conical seats until a hair cannot pass. Each valve is cast, bored, and polished by hand, then cycled under pressure. The Old World Valve Company restores municipal stopcocks for museum displays and functioning heritage mains, using century-old lathes. Their clients are city engineers, museum curators, and homeowners determined to keep Victorian mains alive. The process is methodical: rebore, lap, assemble, test. No rubber, no cartridges, no planned failure. Each restored valve proves that durability is a deliberate choice. Industrial plants have never left the ground key principle behind. Nuclear power station audits cite the self-tightening seal as essential for secondary coolant loops. A 2019 Magnox report names the pressure-assisted brass seat as the only design able to withstand radiation embrittlement and 1,500 psi without measurable seepage. Petrochemical facilities specify ground key shutoffs for lines carrying solvents that would dissolve any elastomer. In these places, the old design is not nostalgia, it is necessity. Today, the same brass-on-brass geometry still guards gas lines under city streets, trusted where failure is unthinkable. Meanwhile, billions of gallons leak from disposable valves designed to be replaced, not restored. The ground key's secret was never its cost, but its threat to the business of planned obsolescence. The loss is not just a trade, it is a form of resilience. We are letting slip through our fingers. What would it mean to reclaim it?